figure out what you're going to do. This is what you need if you can understand what came out of your experiment, because this is what's really in there. So when I kick something, it's going to reflect this reality, not my nice cookie.
What's the significance in that picture there of the fact that that arrow is pointing to that small d?
Oh.
So it seems like the only difference between a proton and a neutron, according to this picture, is that the d substitutes for the u.
That is correct.
That's it?
That's it. That is the difference. Well, that's the difference in what they're composed of. There are consequences to that, which is to the charge. But that's really it, and then the mass a little bit as well. Which brings me, actually, nicely to the weak force.
So
Yeah.
you were talking about the strong force when you relate to the Nobel Prize, and I wanted to understand if the strong force was what keep them together, or is what substitute coming from outside to actually make them pair again?
It's both. It does. It's the thing that keeps them together. It's the thing that keeps the internal components of the nucleus together, the protons and neutrons, even though they should normally repel or just bounce off. And it is also, it's that need, that color force is what creates these things to pop out of nowhere, just pop out of the energy in the way that they do in order to make sure we have everything colorless. So the theory of just in case you see the words, I won't use them much, but QCD is what we call the theory of the strong force. It's quantum chromodynamics, chromo for color. The electromagnetic force, this is finally being clever again, is QED, which is quantum electrodynamics. This is actually, originally have quantum electrodynamics, then quantum chromodynamics for color, and in the weak force, which we're going to talk about now, this is not generally used, but you'll see it occasionally, quantum flavor dynamics, because what the weak force is able to do is change the flavor of these things. It's the only way that can happen. So, we get to the weak force. The weak force can change flavor. Let's remember what that means. I have this chart. The different quarks here are different flavors. So what we talk about is I can create a pair of things from the strong force, a DD bar, but I don't have any way through all the interactions that I've named, the deep inelastic scattering I'm talking about, something comes in, it gets smashed into pieces, and I can pop out pairs of things, matched pairs, particle-antiparticle pairs. I don't have a force yet that allows me to change from one of these things to another, from an up to a down, for example. What allows that to happen is the weak force, that is flavor change. And that is, even though it's this sort of obscure quark picture, it is, the weak force is probably the most relevant to things that we see in life normally. The reason is because that's what's responsible for beta decay. Beta decay is, it's called beta decay for historical reasons. There was this beta radiation, which is really just electrons, but if you don't know that ahead of time, you give things new names, and so we have redundant names for the same things. But beta decay is where I go from a neutron to a proton. So that's what we see, that's fairly observable. One of the ways that's most famously observable is where I go from carbon to nitrogen. Right. In both cases, I have a total of 14 protons and neutrons, but I've changed a proton to a neutron. And, the other way around. The way I've done that, what this is then, is carbon decay. Radiocarbon dating depends on knowing this process. I have carbon-14 is radioactive, slightly. We all have a certain amount of carbon-14 in us that we're getting from the atmosphere. When we die, we stop accumulating it and it starts decaying. And so we're able to see how old something is based on what the ratio of carbon-14 to other carbon there is there. So that radiocarbon dating, whenever there's any of these excavations, and they find like the oldest tomb somewhere, whatever it is, and they tell you how it's 10,000 years old, whatever it is, over a certain range that it supplies. They can be very accurate with that. The reason they can be accurate with that is because of this process is well known. And what this process is, that radiocarbon dating process, is the change of flavor between up quarks and down quarks. I'm going from a neutron to a proton. I'm going from an up, down to a up, down, which means I've taken one up quark, changed it to a down quark. And that's the process we're really seeing there. The result of this is that the lifetime this is a weak process, the weak force. Strong force, strong and weak force is weak. Strong force happens much faster than the weak force. The result is that if I have a neutron by itself sitting here, it will live about 15 minutes. 15 minutes is an extraordinarily long lifetime for these kinds of processes. Usually we're talking about tiny fractions of seconds. And one contribution to that is that the two particles, the proton and neutron, are not very different, or the up and down quark are not very different in mass. So there's not a huge pressure making a change. But the big contributor is the fact this is the weak process. The weak process moves much, much more slowly than anything else apart from it.
Just, I'm confused. You said that the beta decay is where the neutron changes to a proton,
Right.
but the third line down, you drew a proton changing to a neutron? Up, down?
If I have energy, these processes can go in either direction. There's no directionality to what happens. So it's called inverse beta decay, but it's not a different process. Anything can happen in any direction as long as I have the energy for it. So if I have a neutron sitting there by itself, it can decay into a proton because the neutron is heavier than the proton. A proton sitting there by itself can't just decay into a neutron because it would need more energy to be able to make something that's more massive. But the process can happen if I have an electron coming in, or some way to get energy into it, then that's when that process would happen. Brian?
What's the process by which a living organism is somehow changing, affecting it, that stops happening?
It's not. You're breathing. The carbon-14 is in the world around you. So every time you eat and breathe, you're constantly replenishing your supply and keeping it balanced. When you die and you stop those biological processes, it essentially freezes and only decays. You're not taking any new carbon-14 together.
Couldn't a proton turn into a neutron using the explosions that's within it already? Like let's say it takes an
no.
explosion that was between the two
No, you need.
matter and antimatter, and then
That is, those explosions that are in there are just what gives the proton the mass that it has in the first place.
okay.
So it's important that it can't, because that is what makes the proton the mass it is. So I need something extra to get to the neutron. The neutron has that extra from the explosions, and that's why it's able to go the other way. So if I have other examples of the weak force in action that are relevant to us are if I have a kaon here, a K plus that decays, I can have a kaon go to, let's say, 3 pions. What's happening in that case is the kaon is an up, this particular kaon I'm going to use is an up in a strange part, an up in an anti-strange. The up, I'm just going to draw, goes from here to there, nothing changes. It's called the spectator quark. It's going to sit there and watch. The strange is going to decay. It's going to go through first a W particle, which is this guy here, one of my force mediators. And then that W is going to go to 2 particles, a D bar and up. And in the meantime, I'm going to have, because I got a lot of energy here, the K is much heavier, coming from here, when the W comes off, I have U bar, and then I have the D bar D pair that comes out of my X range. Okay, so this looks like a little bit of a mess, but what I have is, this thing is my K, and then here I have different pi's, my 3 pi orbitals. So I had the kaon. The kaon had the strange quark. The strange quark is heavy, and it decays via the weak force into this D particle here. What I'm doing in this is I'm moving from strange to something that's not strange, to these other flavored quarks. The only thing that can move me from strange to not strange is the weak force. I can't do it through any other process. It's because of that, because I have to go through this W. This W is the mediator, W's and Z's are the mediators of the weak force here. because I have that restriction, I can only go through the weak force if I want to change flavor. This kaon lives much longer than it should, much longer than you expect. That long lifetime is why it was called strange. That's why it was given the property of strangeness. Before we knew about the quarks, it was very strange that this thing would live that long. And that's the kaon. The other interaction, which I probably should have started with because it's a little simpler, is the decay of a pion. Let's see, I can have a pi plus, which is going to be a U bar D. So it's the pi minus. And I have a pi zero, which is a UU bar. It's actually a half a UU bar and half a DD bar at the same time. The UD bar can go to a muon and a mu neutrino, whereas the UU bar, these two come together, they can make 2 photons. So the UU bar, we talked about this before, they'll crash into each other and annihilate. Right? I'll get the energy off, and that energy comes off as 2 photons. That is an electromechanical process. Sorry, electrodynamic process. It's electricity and magnetism. So that's a photon. If I have a pi minus, has a UD bar, and I go to something else, a muon, that's this guy here, muon and a mu neutrino. When I do that, that is a weak process because I'm changing the flavors of things. I'm getting rid of flavors. And this thing then lasts much less time. The lifetimes for these two events are very different. One because it proceeds through the weak process, and the other because it goes through the electromagnetic process. So by seeing how long things last, you can see which interactions are responsible for it.
Can any quark just go into any quark?
Any quark? Okay. These can go into, normally through the weak process, what you'd be allowed to do is go from, say, within the generation, so up and down, or strange, something like that. You are allowed to cross the generations through what's called a mixing of this. There's a little bit of mixing here, because these things aren't really what they are. Let's see if now's the... it always gets trickier. Might as well go to that now. Let's see. Okay, it's time for that question. So, here's where we go with this. Yep.
We talk about the subatomic level.
Right.
When you talk about a neutron decaying into a proton,
Right.
you've affected the atomic level. It's not your charges on.
Yes, I have.
Don't you need an electron to balance it?
That'll happen by itself if it wants to. It's what I'll have is an imbalance. I'll have an ion that wants another electron or has one electron too many, and then there'll be chemical consequences to that. Something may happen, but it's I don't create a force where something has to happen in that case. I want the other electron. The only thing that really creates that need for something to happen is the strong force, because I have to be colorless. I can't violate that, and so things then are required to happen. But with everything else, you just have this desire, and you float around looking for a partner to meet your need, essentially.
So, Josh, how do you set up an experiment to really see these decays?
That we're going to get to in about 5 to 10 minutes as soon as I get through the mixing here. So what we talk about these as being separate particles, but there are really 2 ways to think of this. One is the particle is its own flavor, that we've been talking about. The other is in terms of mass. It turns out that I can have these flavors, but I can also write them as combinations of masses rather than flavors. So instead of calling this a D, I can call it a 4.8. Instead of calling this an S, I'll call it a 95. And the way quantum mechanics works is I can either name them by their mass or I can name them by their flavor. Either of those things is okay, but they're not really the same. Each mass is really a combination of these three flavors across the generations. And each flavor is really a combination of the three masses. Now, the best analogy for this is the turnpike. The turnpike, the New Jersey Turnpike, is car and truck lanes in one area. And then it switches to the eastern and western spurs of the turnpike. And there's that place you go through where it crosses. So I have trucks on this side, cars on that side in the south, and then when I get further north, I have the eastern traffic and the western traffic. It's the same turnpike. I have two of them in both cases. But in one case, I've characterized it as cars versus trucks. In the other case, I've characterized it as east versus west. And it doesn't make sense to say, well, how many trucks, to talk about the trucks on the east and west with cars in that split. I've divided it one way or another. Right? I can't say how much carness is in the eastern spur or the western spur. They don't have anything to do with carness or truckness. I'm just changing from one way of looking at it to the other way of looking at it. All the traffic is the same, everything is the same, but I've shifted how I'm defining these things. And that's what happens here with parks. The consequence of that is because there is that bit of mixing, I'm able to move diagonally. I'm able to shift from one generation to the next, because these aren't pure states. This is not a pure down. This is really down with a little bit of strange and bottom mixed into it. And the reason that happens is because I have that mass, because I can characterize it as mass. This comes up as a question with the leptons. And remember, you may remember, I said it quickly last time, these things I can move around between one and the other, but with the leptons I have independent conservation of lepton. That means, that's why I have three different kinds of neutrinos here. For an electron, that goes along with its electron neutrino. And if I am creating an electron or doing any kind of interaction, I can't destroy an electron without creating either another electron or electron neutrino to balance out. I have to have the same number of electron and electron neutrinos at the beginning that I have at the end. So this is, and I can't move from an electron to a muon neutrino. I can't change across here. That's the way it always was. And that's because the neutrinos were thought not to have mass. If they don't have mass, then I don't have two ways of looking at it. I can't say, well, I can look at these as mass states or as neutrino flavors. There's only one way, if the mass is all zero. So this one, it doesn't contain parts of these other ones. It would just be purely an electron neutrino if there's no mass. But it turns out, in some number of recent years, these things do have a tiny bit of mass and are able to move from one to the other. And we see that, one of the ways that first came up was with the solar neutrino deficit, which is another one of these big crises. The sun, the standard solar model, the sun is extremely well understood. Not the solar weather on the outside, but the actual nuclear processes on the inside are very well understood. So we know exactly how many neutrinos of each type should be coming out of the sun, and we weren't getting the right types. They weren't showing up. We had too many of one and not enough of the other, and this was a big problem. This was the solar neutrino deficit. Nobody could figure out why, although people sort of suspected it was because of this mass mixing, but nobody had been able to measure the mass. One way to figure this out was to look for a day-night effect. If I put a neutrino detector on one side of the Earth, when it's facing the sun, I'll see a certain number of neutrinos. And at night, when the Earth is in between the detector and the sun, all the neutrinos have to go through the Earth. If there is some mass to these things, then the fact that they're going through all that matter in the Earth would help trigger them to shift from one to the other. So if you see a difference in the ratios of neutrinos during the day and the night, because you're going through the Earth, you're not going through the Earth, that will be the indication you have mass. So that's what we did. That's how we figured that out.
So couldn't everything just decay? Couldn't everything decay to neutrinos, assuming it wasn't a neutrino to begin with? Not a neutrino, but a neutrino and its counterpart. So a muon and a muon neutrino.
These things happen. Everything can't, because you have to conserve. You'll have energy around, and that energy's got to go somewhere, and it will tend to just pop out in particles. And that's what happens. So there's a certain set of processes that are allowed. It's finally said anything that's not prohibited is required. So these things are going to happen all the time in different ways. So the way we know this stuff is from building big machines to test it. We started out with cosmic rays. then you're just subject to what occurs naturally, what you can see. We did actually get this far with cosmic rays. All these things are coming out of the sky. You need more energy to find more exotic particles, and you need to see more of them than you can get just by observing. So we build particle accelerators. There's a couple different types. The biggest difference is a linear accelerator and a ring. And these are two examples. This is SLAC in California, near Stanford, the Stanford Linear Accelerator Center. And this is the longest, straightest object in the world. It's famous for. It's a couple miles long, and it's just one very long, very straight beam of electrons. It comes up here, and then where it breaks out here is where you see all the different experiments there. So I'm taking my electrons, and I'm just racing them as fast as I can, and there's a set of magnets in here, and that makes them go faster and faster and faster, and I get the highest energies I can. You can make these things much smaller, but you need them longer if you want to keep getting electrons to go faster, smash them into things, or occasionally into each other, and then I can do my experiments here with electrons. This is Fermilab in Chicago, the Chicagoland.
What's the name again?
Fermilab, the Fermi National Accelerator Lab, whatever it's called, Fermilab. This is now a series of rings. And this one I have electrons and positrons. Because electrons are light, if you start carving them, they lose a lot of their energy. They start throwing off all kinds of radiation. Anything charged will do that, but because electrons are so light, that limits how fast you can, what the benefit is, how fast you can make them go, because they're giving off energy when you curve them. So we do the electrons in a straight line in a linear accelerator. It doesn't have to be that way, but that's the best way to do it. For protons and antiprotons, we make them go in a ring, because then you can keep getting them faster and faster and faster and faster, and just keep going. The losses due to curving them are not that big, but it does mean to minimize those losses, you need the ring that you're curving them around to be very big. So this is a couple miles across. There is a herd of buffalo that roams in the middle of this, which is the Fermilab buffalo. There are also albino deer that roam around outside the ring, contained within the perimeter fence there. So if you go there, one of the things to do is look at the buffalo and the albino deer. There's a canal across the top here, which is really cooling water. This thing is underground, not hugely underground, but down in a tunnel beneath. What happens here is the protons and antiprotons are manufactured. They get started in the small ring, they get put into the big ring, which is also a storage ring. And I have a beam of protons going this way and a beam of antiprotons going that way, and they just go around and around and around, and I get more and more of them, and they go faster and faster. And then at a couple of points, I can do two things now. I can either take a few of them, open the valve, and let them shoot out straight. They come out here, and then this is the array of fixed target experiments where I shoot the beam straight into a target and see what splatters out on the other side. And then I have 2 points around the ring, places where I cross the beams. I have the proton beam going this way, the antiproton beam going that way, and I have them cross. And when they cross, some of them will collide. When they collide, that's where I get all my exciting physics that happens, and I surround that with a big detector. So I have a set of detectors here for the fixed target experiments, and I have a pair of detectors there for the collider experiments. This is the other aerial view there. Again, that's a couple miles across. And if you want to see a picture of what it looks like from the ground, there's the main office building that's over here. This is a picture of my wife from a newspaper when she bought her car in graduate school. It had the slogan that it doesn't take a rocket scientist to figure out a Saturn is a great value. She is standing in front of the main building at Fermilab. She made the papers. So that brings us to, this is inside the ring. This is what it looks like. This is, I don't know, 10, 15 feet underground. The canal is above top here. And these are magnets. And you see it doesn't curve very much because it's got a couple miles to go to get all the way around. And the beam is running through a pipe, a vacuum pipe that's inside there. So the protons are going one way and the neutrons, or the antiprotons are running around the other way through this storage room. And you can go down and go around in circles on it this way. Then we need to be able to detect this stuff. So there's a set of detectors, which we'll talk about for the rest of the time today. There's anything else here. The first thing, the most obvious, the most conceptually simple, and the oldest, is the bubble chamber. To make a bubble chamber, I take something that's about to boil. Usually use hydrogen, also because hydrogen is or a hydrogen atom is just a proton with an electron flying around it. The electron is light and small and essentially irrelevant. So I have a proton here in the middle, which is 2 up and down quark, sitting there in the middle. And I can make, if I just have hydrogen, it makes a nice target. I know whatever I hit, it's going to be a proton. So I can do both the detector and my target is the same thing. So I have this tank of liquid. The liquid I keep through just old style physics with a piston, right at the verge of boil, just about to boil. So if anything goes in there, if I get any energy out, it's going to start boiling. It's going to start making the little bubbles as it goes through. So I keep it right on the, I'll get a path of bubbles from any charged particle that moves through. If it's not charged, it won't do that. There won't be any interaction there. And then I put the whole thing in a magnetic field. Why do I do that? Because if I've got a charged particle going through a magnetic field, it's going to curve. Because the magnet will interact with the electric field that the particle makes as it goes, and that will cause it to curve. If it's positively charged, it'll curve one way. If it's negatively charged, it'll curve the other way. So I can tell if something is positive or negative based on which way it curves. I can also tell what its momentum is, which is a combination of its speed and its mass. Most of these things are coming in at the same speed if they're coming from an accelerator, so I can really see what the mass of the particle is based on how tight the curve is in that magnetic field. So my beam comes in from one of these accelerators. It hits something, which is going to be the proton in the middle of the hydrogen. Something is going to happen. I watch what that is, and then I take a picture, an actual photograph. I've got a camera here with a big flash on it. If I'm getting more sophisticated, I put them from different angles because this is a 3D picture. And I take a snapshot. I time the beam. I pulse the beam that comes in, and every time a beam pulses, I take a photograph. And that's my experiment. That's my detector. And it looks like this. So these are actual photographic film from bulb chambers. And one of the exercises you do in sometimes grad school is to go through these films and look at them and try to find these different particles here. And it's a great thing to do because you're actually seeing these interactions take place. In this case, this is a picture of an electron. So we're going to have a magnetic field. The electron is fairly light, so it makes a tight curve. And because it's going through all this hydrogen, it is losing energy as it goes. So it spirals in. It doesn't just go in a circle. So my electron came from somewhere, and it kind of spirals in until it runs out of energy and stops. And all these other little things are electrons. It tells me two things. I tune my magnetic field so an electron will look like this. If I have a smaller magnetic field, it will kind of curve gently. I don't want that. I want a nice tight spiral for my electron. I can figure out from the electrons, this one had more energy than these to start with because it was able to make a bigger loop. It had more momentum. I can also tell which direction the magnetic field is because I know electrons are negative. So I know anything negative is going to spiral this way. It's not always true in these pictures. It depends how things were arranged. I might flip the magnetic field just to make sure things stay balanced, in which case I need to be able to find the electrons to figure out which way my magnetic field is pointing. So that's just a picture of an electron. In this case, I have a photon, which has created an electron-positron pair. This is this pair creation, pair production. So I have a photon coming through. Cover a piece of chalk. The photon had a lot of energy, so it created an electron-positron pair. That's right here. The photon is not charged. It's not going to make the bubbles. Only charged particles make the bubbles. So it was coming here, where my stick is, and then at this point is when it did the pair creation. The electron went this way, the positron went that way. Again, they're tight spirals because they're electrons and they're light. They go in opposite directions because they have opposite charges. And I can see from here where the photon was coming from. It must have been coming from here because that's where the momentum of these things had. They're going to be traveling in the same direction that the thing that produced them was coming from. Because that's where the momentum is. So that's my basic example of this pair production. Okay. You can see there's lots of other things going on here. And most of these things are cosmic rays.
On the photo on the left, are the straight lines, the vertical straight lines and the X's drawn in, or those are from something?
The X's are drawn in. The straight lines are cosmic rays. And they're actually not straight. If you look closely or hold a ruler to it, you'll see that they do curve. They're going, for the most part, to be muons coming in from, either muons or pions, they're coming in with a lot of energy from space.
So those are designation of cosmic rays because you're inside an experiment, technically there is no cosmic rays unless you're talking about that the cosmic rays went through all these two.
Cosmic rays are coming through you, through the Earth, through everything all the time.
Okay, so that's what you're detecting.